acknowledge my two collaborators, Alex Sims and Kate Swanger. They are the geologic brains behind this work. I'm just the dating brain, they are the geologic brains. And I also want to acknowledge funding through the National Science Foundation. So I want to take you to a completely different place. I want to take you to the bottom of this world, to Antarctica. And I hope that it actually induces some cooling thoughts and we all feel nice in here. Okay, so I first want to talk a little about why we're actually interested in Antarctica. Then I want to review some work that has been done with regard to luminescence dating in Antarctica. And then I want to take you to two special places where our group has done work, which is the Antarctic Peninsula and the McMurdo Dry Valleys. Okay, let's first look at the continent. Antarctica is at the bottom of the world, which is why most of the time we just see it as this white shapeless thing at the bottom of a map. Actually, it is a continent. It has twice the size of Australia, or larger than the United States and Mexico combined. It is separated into two halves by this mountain range, the Trans-Antarctic Mountains. So it's split into West Antarctica and East Antarctica. And one of the dominant features is the Antarctic Peninsula here, which juts out from the continent. As far as the globe is concerned, the Antarctic Peninsula is here, and then a little further north would be South America. So if you want to go there, you fly to Chile, and then you take a boat to go to the Antarctic Peninsula. Antarctica is also the coldest, driest, and windiest place on Earth. So why would we be interested in doing dating there? Well, 90% of the surface are covered in ice. And this means that Antarctica holds about 61% of all the fresh water that is available on Earth. And not only that, if this ice sheet were to melt, it would contribute to 58 meters of sea level rise around the globe. So we would be in seriously bad shape if that happened. Now, of course, we know that temperatures are getting warmer, that climate is changing, and we want to know, or at least try to predict, how much of this ice will melt and how much sea levels will rise. Now, in order to predict the future, we like to look at the past. We like to see how much climate change happened in the past, how did it affect the Antarctic ice sheet, and how did this contribute to sea level rise. Now, we have here a keyword that is past climate. When we look at past events, we need some form of dating. And that's where OSL dating of sediments and rocks comes in. Okay, so most of the continent is covered in ice, so we actually have a hard time finding sediments and rocks. Now, where can we find them? There are two places. One is the Antarctic Peninsula, right here. And then there are a few other places along the coast. And then there are these remarkable McMurdo Dry Valleys right here. And in my presentation, I want to take you to both of these places because we have done work at both of these places. Okay, I know you know all about OSL and TL, but you might not know all the details of luminescence dating. So the dosimeters that we use are actually quartz and feldspar. We work with natural minerals. When they are buried in the ground, they're exposed to natural radioactivity. So over time, they accumulate trapped charges. Now, by some event, it can be wind or water, this covering layer is removed, the grain is exposed to sunlight, and it gets transported to another place. As it gets transported, all the trapped charges are emptied. Eventually, the grain is deposited, it accumulates a new trapped charge population. Eventually, we will come and then we determine an age. Now, we use OSL to determine the dose. We measure the radioactive nuclides to determine the dose rate, and we take dose and dose rate to determine an age. age is always the time since the last sunlight exposure. The age range that we can cover depends very much on your location, but it's roughly 10 years to 500,000 years. And the uncertainty is pretty much independent of the age, it's 10%. Now, we have some very trivial key criteria, but they become important for our work. First of all, the minerals must have sufficient signal so that we can actually measure a dose, and they need to be completely reset prior to burial, because if they have some residual dose, we will overestimate the age. When you do dating, people tend to smile about you a little and don't take you very seriously because they think you're not doing dosimetry. Actually, I like to believe that we do dosimetry under severe conditions because we use dosimeters that behave differently every single time we want to use them. And not only that, we work in radiation fields that are not very well characterized at the present. And on top of that, we want to extrapolate them over thousands or maybe even hundreds of thousands of years in the past. So yes, we do dosimetry, and it's hard work. Okay, when you go to dating conferences, there are endless discussions about the best dating procedures. We have so many procedures now and so many acronyms that it would actually be nice to have a dictionary. So I decided not to go into the nitty-gritty of all the dating procedures. Instead, I want to focus on my presentation why we actually do what we do. So let's look at the past work that has been done in Antarctica. When you Google or when you use a search engine and you look for the keywords luminescence dating and Antarctica, you find roughly 30 papers. Now, of course, I can't mention all these papers in detail, so I want to make specific groups and tell you what those are about. Okay, so let's start with the very first papers. The first one was published by a German group in 1997. It was followed by a paper by a US group in 2001, and another one from the same year by a group in Australia, New Zealand, and England. And what those three papers have in common is they were the first papers, so they actually looked if Antarctic sediments are even suitable for luminescence dating. And what these three papers found is actually relevant for all the following work that has been done. What they found is that feldspar in Antarctica is very bright and nice, and it even works in some of the places, but one of the big problems is that it is often not sufficiently reset. So it's not zeroed, which means the ages that we measure with feldspar generally are overestimated. They are too old. On the other hand, quartz is wonderful. It's very well bleached. It has only a small problem. It has no signal. So sometimes you're lucky and you find quartz with a low signal, but generally quartz has no signal at all. I have copied here some figures from a paper by Glenn Berger. He actually tried to do single grain dating on quartz. So he used single grains of quartz, tried to date them. And we know that even in very good deposits, only about 5% of the quartz grains have a usable signal. The others are just useless. I want to draw your attention to the numbers I have highlighted here in red. So this was a pretty decent sample. He measured 2,000 grains to get about 50 okay ones. So that's not too bad. But when we look at these, and these are much more typical, he had to measure 3,000 grains to get 7, or 5,000 grains to get 18. So you get a feel for what it means to date quartz in Antarctica. And this is a problem that all subsequent work has faced. Okay, so we can group all the subsequent papers into three main categories based on their applications. The first one is Antarctica is often used as an analog for Mars. As I mentioned, it is the coldest, driest, and windiest place on Earth, so it matches Mars pretty well. Here we have a picture that was actually taken in the Antarctic dry valleys. And here is a picture of Mars. So you can see there is not that much difference. These two papers looked at the motion of dunes in the Antarctic dry valleys and the formation of ice in the subsurface. The next group of papers actually deals with climate. So they want to know how temperature change influences the glaciers. So if they advance or if they retreat. These publications studied glaciers. And the third group looks at Antarctic beaches and sea level change. And this is where our work comes in, and that's what I want to talk about in a little more detail. But we have to take a small detour. We actually have to understand what beaches have to do with sea level change. Okay, so we have here a map of Antarctica that has some colorful spots, and those are ice shelves. Now, how is an ice shelf defined? We have here ice that is still on the continent. It is connected to the ground, and that's what we simply refer to as grounded ice. But where the ice meets the ocean, eventually you will have water underneath the ice. The ice floats on the water, and that's where the ice shelf starts. Now here are two pictures. This is the Ross ice shelf, the largest one, and marked in red. So this is where you have the transition from the continent to the ice shelf. Ice shelves can be up to 1 kilometer thick, and we have to remember that 9/10 will be submerged. We can only see 1/10. So this is what you would see if you approached it from the ocean side. Now, why do we care about ice shelves? The term ice shelf actually became widely known in 2002. We had here the Larsen B ice shelf, and within a month, it pretty much disappeared. So in January, at the end of January, it was still that big. In March, it had pretty much totally collapsed and was gone. We're talking about the size twice the area of Mexico City. Within a month, it was suddenly gone. Now, why do we care? You all know when you have a glass of water and you have some ice cubes floating in that water and the ice melts, nothing happens. The level of the water in the glass will not change. So actually, we are not concerned about the breakup of these ice shelves because they are already floating on the ocean. They do not contribute to sea level rise. So this is actually not our problem. In order to understand the problem, we have to take a bigger look at the continent. The Antarctic plateau is at a height of about 3,000 meters. And so you have here the Antarctic plateau. Down here you have sea level, and we have glaciers that are flowing down. Now you can see there is quite a difference in height, which means there's quite a bit of force behind these glaciers. They are pushing. And the only thing that's holding them back is the ice shelf. Now, if you remove the ice shelf, there is nothing that holds back these glaciers. They will just flow into the ocean and add more water, add more ice to the water. So if you have a glass of water and you add more ice, that's when the problems start, because that's when your water level actually rises. There's a slightly different picture that we can use to describe this. We have here the continents, and it's a very simplified picture, but the continents in essence float on the mantle. The mantle is a very viscous fluid. Imagine a piece of wood floating on honey. I think that would be a good description. So here we have Antarctica, and it is pushed down by the weight of the ice into the mantle. Now, of course, if we remove some of that ice, because it's no longer held back, first of all, we add a lot of ice to the water and sea levels will rise. But there's another thing that happens. Imagine your piece of wood floating on the honey and you push it down and suddenly you take your finger away. The piece of wood will slowly start to rise. And the same thing actually happens to the continent. As the ice melts off the continent starts to rise. And this is not just something theoretical. We can measure this. So let's go back to our Larsen B ice shelf. We have here the Antarctic Peninsula. This is the location where Larsen B used to be. And then here at this dot is Palmer Station. Palmer Station is one of the US research stations, and the altitude has been monitored by GPS. So let's look at the graph, and we can see that the altitude was fairly constant, and then suddenly after the year 2002, it started to rise steeply. So initially the uplift rate was 0.08 millimeters per year, and after the breakup of Larsen B, it suddenly went to 6 to 9 millimeters per year. In geologic terms, that's like a race car. I mean, it's just like nothing. Okay, so this is the end of the detour. That explains why we're interested in Antarctic beaches. So now let's come back to our work. Our question was, is this actually unprecedented or has this happened in the past? So our idea is we have here a beach, and if the ice melts, the continent will start rising. So what was originally a beach will now be at a higher level, and then again at a higher level. And there are actually sites where you can see up to 40 levels of these raised beaches. So our idea was, if we can date these beaches, we can figure out how fast the continent rises, and then some geologic modeling can determine how much ice had melted. So in order to do that, we need the rates of uplift in the past. Again, we have two keywords. We have rate and we have past. And that's, again, where OSL comes in. We have one small problem with these beaches. They are not nice sandy beaches, so we cannot just go there and collect sand like we usually do for luminescence dating. We actually have beaches that consist of cobbles. So our idea was that while these cobbles are at sea level, the waves will permanently turn them around, which means the whole entire outer side is actually bleached and exposed to sunlight. However, as the continent starts to rise, those cobbles just sit there, and the underside of the cobbles is now in the dark. So by dating the underside of the cobble, we actually know how old this beach is. If we measure the height, we can get an uplift rate. So Alex Sims had multiple grants funded to do work in the Antarctic Peninsula. We collected samples on multiple beaches along the peninsula. Here are some pictures. So we're only interested in the underside. So first the cobbles are marked so that we know exactly which one the upper side and which one the underside is. And then here is actually Alex, and this is my graduate student, Chris. So they had to go there, they had to crawl under a tarp, remove this cobble in the dark, wrap it, and then they could come out from under the tarp. Usually, or always, this work is performed in Antarctic summer, but that does not mean it's nice. So this was actually in the middle of Antarctic summer, and my student decided to never ever go back. He was done after one time. So we bring the samples back to our lab, and our first job was to develop a dating method because we had cobbles and not sediments. So what we decided to do was we cut the cobbles into cubes, and then we sliced off the very surface of these cobbles because our theory was that this would be exposed to sunlight and bleached. So this is the part that we want to date. We crushed it carefully, and then we treated it like sediment to isolate quartz and feldspar. Here are some pictures of Antarctic rocks, and they are actually not very well suited for dating. It's very hard to separate quartz and feldspar, and sometimes it's even hard to find quartz and feldspar. The first study we did was in the South Shetland Islands. We identified some glaciation between 1500 and 1700 AD, and that was synchronous with something we call the Little Ice Age in the Northern Hemisphere. So this was a period of unusually low temperatures, and it seems that at the same time Antarctic glaciers progressed. So this was very promising because this told us that our method actually works. So then we did more work at other sites. And so what we have here is a figure that shows elevation of the beach versus age. And we would, of course, expect that a higher beach is also older. So the orange dots agree with this very nicely. The problem is that the orange dots are not OSL ages. They're actually radiocarbon ages. The OSL ages are the blue dots, and you can see they're all over the place. So imagine 2 years of work and that's the result. It's not very encouraging, but Antarctic cobbles are hard to date, and that was our conclusion. Dating Antarctic rocks is simply hard. It works very well in some locations and not so well in others. Okay, in the last couple minutes, I want to take you to the McMurdo Dry Valleys. So the McMurdo Dry Valleys are located here. This is the Ross Ice Shelf, that red spot that we had in a previous map. Here is McMurdo Station. It is a US research station. It's the largest station in Antarctica, has about 1,000 people in summer. And then very close to the McMurdo Station are the Antarctic Dry Valleys. If you want to go there, you go to New Zealand, you jump on an airplane, and then you fly over to Antarctica. This is the Ross Ice Shelf, and there is actually an airport on the ice shelf. You land there, you hop onto one of these buses, which then takes you to McMurdo Station, which you can see right here. It looks like a mining station. It's not very pretty, but that's where you gear up, you collect everything you need, then you jump again on a helicopter and you fly over to the McMurdo Dry Valleys. So these are the trans-Antarctic mountains that I had shown before, and there is the small region of valleys which are dry. There is no ice there. They're pretty remarkable. So this was the camp. We were there for 4 weeks, and I want to draw your attention to the facilities. So we had a living camp, a sleeping pen, and this was our bathroom. And we did this for 4 weeks. So this is one of these valleys. It's called Pierce Valley. It's actually one of the smaller ones. And you can see there are glaciers coming down. And these glaciers is what we're interested in. The rest of this valley is completely dry. There's almost no precipitation ever. Okay, why are we interested in these valleys? We actually want to know if the glaciers have different rates of melting. You can see there are some small meltwater streams. So calling it stream is actually a little exaggerated. It's really, you could jump over them and they're maybe that deep. So it's not exactly a stream. But we have here the meltwater. And our idea was if we can date the sediment that was deposited by these streams, or maybe even the sediment in the ice, then we can say something about past climate. Just very briefly, this is an ongoing study. We collected samples earlier. My postdoc went last fall. He will go back again this fall. We were able to find that different fans have different ages. What we really want are depth profiles. Some sites work pretty well, with the exception for this sample. We have a nice age sequence. Other sites do not work so well. We have age inversions. We think that these samples were contaminated when we took them. So when you are in Antarctica for 4 weeks, all you see is sand, you see rocks, and you see ice, and eventually you start missing things. You form a very tight connection with the rocks. So eventually they become your substitute pets. After a little more time, you actually think they're talking to you and watching you. And at the end, you wonder if you can eat. And that's the point where you know you have to go home. So thank you very much. I want to thank the organizers, NSF for funding, and my collaborators. Thank you.
Thank you, Irina, for the very, very interesting talk. We have a question.
Thank you. No, I just had a question regarding the proportion of radioactivity in your samples. And just a comment that Derek Sears has collected a lot of meteorites and characterized them from Antarctica. I'm sure you know about that. Yeah.
Yeah, I had a slide in there where I was going to show some papers, but we were running out of time. Yes. Oh, so that's actually not that different from other places on Earth. It's roughly 1% potassium. We have a little more than 1%, 1 ppm uranium, and maybe 5 ppm thorium. So very normal, nothing unusual.
Any more questions? Yeah.
Thank you very much for the presentation. It was amazing. I'm wondering, quartz is something that is broadly used for OSL dating in so many places. Why doesn't have signal in Antarctica specifically?
That is an excellent question. We know that quartz from polar regions in general is not very good. So if you go to the Arctic, you have the same problem. We know that quartz gets better if it goes through multiple periods of deposition and bleaching. So we think one of the theories is that the transport distances are simply too short. It never has the chance to sensitize. That's one of the theories. We don't know.
With this, I'm expressing my thanks to Ringna covering the very nice topic, unknown territory.